I want to work through an example now where we're focused on the vector nature of the electric field. So if you look at this problem statement, it says find E, the vector, at x equals 4 meters, y equals 3 meters, and solve for the components Ex and Ey. So you might remember from earlier discussions in school about Cartesian grids and probably from trigonometry, and you might remember the Pythagorean theorem that will connect the displacement from two components. And in our example, the components are the displacement x and y. So this value r, that is our only unknown if we assume the source charge is 1 coulomb, this value r can be solved if we know x and y. So if I just write down a quick reference, and the reference is, of course, is r squared equals x squared plus y squared. So graphically, I'll just put some tick marks here, 1, 2, let's say 3, and 4. So this would be x equals 4 if we go out to this point. And now I'll go up 1, 2, 3. Same thing on the y side. So now I've got this y equals 3. We can think of these as sides of a triangle from the displacement. So if I go out 4 and I go up 3, I'll end up with a location that I'll indicate right here. We'll call that the observation point P, and it's going to be indicated with its coordinates P of 4, 3. And that's a very popular technique, of course, to identify the location of that point. So now I know that based on the Pythagorean theorem, I've got my r vector, which is my displacement vector in this case. R is going to equal, this is going to equal, if I just take the square root of both of those sides, r is going to equal the square root of x squared plus y squared. And these are my, this will be my x, this will be a part of the triangle with the y value, so that we know that that's going to be 3. I'll go ahead and write it on this side. It's the same putting it over here as it would be as the projection there. And I already have x equals 4 on this side. So I can just plug these numbers in, and you've probably already done this in your head because this is a very popular triangle. It's the 3, 4, 5 triangle. So I know that r equals the square root. And if I'm just going to leave the units out for now. X equals x at 4 squared is going to be 16, and then y is 3 squared, which is going to be 9, and we know that that's going to be the square root of 25, which is going to be equal to 5. So you probably remember that. So we now have enough information to calculate E once we put in those constants. We'll do that now. So since we've already done a similar problem with the magnitude, I'll run through this pretty quickly, but I'm going to say the electric field, I'll keep the vector sign on it there, is going to equal to, we're going to use Q of 1. So I'm going to, again, I'm ignoring units for the time. I'm going to say 1 over 4 pi epsilon naught. So that's just one big constant that we'll have to calculate, times 1 over, we already know what r squared is. If r is 5, r squared is going to be 25. Okay, and if I recognize that this also is a common, it's commonly referred to as the Coulomb constant, and just from memory, you can punch that into a calculator and verify this. But we also know that this has a value of 8.99 times 10 to the 9 divided by 25. And the value that we come up for this is, we're going to say 3.6 times 10 to the 8. And we're going to say volts per meter. And this is indeed a vector sign here, even if it's a little sloppy. And where's the direction of that? We haven't calculated the x and the y yet. We're leaving it for the time being in the r hat notation. That vector r hat is always pointed radially away from the source charge, and it's a unitless vector. So if I say r hat, that's what this means. So I can say 3.6 times 10 to the 8 volts per meter in the r hat direction.